Welcome back. Today's guest is Dr. Fimbinger, a specialist in applying DEM to the raw materials sector. He uses bonded particle models to model large structures. Hello Eric, it's nice to have you here today.
Thank you. I'm looking forward to sharing how bonded particle modeling can be used in DEM simulations, especially to set up deformable and breakable objects.
Eric, you have mentioned that bonded particle models allow particles to behave as unified, flexible structures rather than rigid objects. Could you explain us in more detail how this model works?
Certainly. To set up a bonded particle model, an advanced contact model is used that is able to connect two particles with a beam-like element, so-called bonds or bondings. Those bonds are able to transmit loads between the particles, resulting in deformation effects or stresses, such as tension, bending, or torsion. And with that, the resulting structure, the bonded particle model, is able to react as a unified, flexible structure rather than a rigid object. Under load, a bonded particle model can handle deformation and, if required, also breakage, when local individual bonds exceed the individual stress limits.
Now, when it comes to this breakage you mentioned, how does this property contribute to the DEM simulations?
For instance, a rock modeled as a bonded particle model is able to break into smaller pieces when subjected to a respective load, with the crack propagating naturally as local bonds exceed their stress limits.
Eric, what are some of the key applications of the bonded particle models, particularly in the raw materials sector?
In the raw materials sector, bonded particle modeling can be used for applications and processes that involve deformable or breakable particles, but furthermore also to model advanced components, system parts. One representative field for applying breakable bonded particles is, of course, crushers, for example, jaw crushers, into which breakable particles are loaded to analyze the functionality or relative efficiency of a certain novel system design. Analyzing such designs in a virtual way is respectively called virtual prototyping. In this analysis, a jaw crusher is shown loaded with bonded particles. The bonds are able to break, as can be seen on the bottom, into smaller fragments. In this detail, you can see the stresses in the bonds from blue to red, with blue indicating low stresses and red indicating high critical stresses leading to breakage. Another potential field for applying bonded particle modeling is conveyor belts. When a conveyor belt is set up as a bonded particle model, it is able to deform dynamically under loads from the bulk material loaded on it.
Okay, I think it's clear that bonded particle models offer a lot of versatility. However, I imagine there are some challenges when simulating breakable or deformable particles. Eric, what are the major challenges to consider?
At first, finding suitable bonded particle definitions with all the required parameters is essential. Similar as for other DEM model definitions, this is required to reflect behavior as intended. Related to that is also the level of simplification. A rock modeled with small particles can ultimately break down into the smallest size this bonded particle is made of. If this is too coarse, the particles are too big, then this model is probably not usable. On the other hand, if the particles are very small, the resolution is very fine, this leads to a lot of small particles and also to a lot of bonds. So with the computationally already expensive small particles, this results to a much more computationally expensive simulation overall. So it is required to balance computational costs with the need for fine detail in deformation or breakage. Ultimately, structuring a certain bonded particle model in a DEM environment should not be ignored either, referring to the actual setting up of a given bonded particle model, meaning placing the particles and the bonds in space to get a certain bonded particle model, either in a rectangular or a regular arrangement, such as for belt conveyors, for example, or also with a specific randomness, for example, to set up raw materials, mineral raw materials, as in the raw materials sector. Set randomness also means to define a certain distribution in the properties of the particles and the bonds with which a bonded particle model is made of, which could be very beneficial for the overall structure.
Speaking of applications, you mentioned conveyor belts earlier. Could you please explain to us how conveyor belts are typically modeled in DEM simulations and how your bonded particle model improves upon such approaches?
Conventionally, conveyor belts are modeled as rigid surfaces with an advanced contact model which induces a movement in particles when they get in contact with the belt's surface. This may work for simple applications, for example, when the belt or the belt's deformability is not in focus, for example, when the belt is only used to feed a system. However, when the belt's flexibility is also in focus, this rigid belt modeling does not work, of course. So when instead set up as a bonded particle model, the belt is able to react dynamically and locally to loads from the bulk material on the belt, as well as to components keeping the belt in place, such as idlers and pulleys. An example of a belt conveyor system where this can be visualized is a sandwich conveyor, where the deformability of the belt is of significant importance. This system transports the material with it clamped between two belts. And of course, the capability to brake can also be implemented into such a belt model's bondings.
So now we have seen two completely different examples. Would you say it's possible to categorize bonded particle models?
I would say there are more forms of categorizing bonded particle models. A very basic one could be, is it used for modeling particles or is it used to model parts or system components? For particles, we already mentioned rocks as from the raw material sector, where breakage is important. Other noteworthy examples could be fibrous goods, such as straw or hay from the agricultural industry, where deformation is more dominant. In this analysis, you can see a swath conditioner, where the bonded particles are forming the fibers going through the system. This analysis was intended to analyze the system for clogging. For parts, we already mentioned conveyor belts, but this approach can easily be applied to the modeling of membranes, textiles, FIBCs, or commonly called big bags. Another categorization could be the dimension of the bonded particle model, where a 1D model refers to a single line of bonded particles, such as for the modeling of wires, ropes, or structures made of those, such as fences or rock protection nets. 2D models means a layer of bonded particles, such as for the modeling of membranes or, as just discussed, for the modeling of conveyor belts. And a 3D bonded particle model would refer to the already mentioned rocks. Additionally, a mix would also be possible, for example, when a big bag is attached with 4 ropes on its edges.
Okay, Eric, thank you for this session. Do you have any final advice for participants who want to use bonded particle models in their work?
Bonded particle modeling is a powerful way to simulate complex behavior in DEM simulations, especially when it comes to deformability or breakage. There is a lot to explore around this approach. I would encourage to explore its potential and creatively think about applications.
Well, I think there will be plenty of applications for bonded particle models in the future. Thank you, Eric, for joining us today, and thanks to all of you for tuning in.